more simple one. That's why I cook it here. I'm trying to teach him after class. I gotta do homework as well. Physics, engineering, this class. And actually that's it. But it's a lot. Yeah. All the lives. Get all this and put it on the sheet. I don't even know if the equations are right. That's crazy. You do individual? I don't know. No, get the formulas right. Then when I start putting the equation, I was like, give me some parentheses. I think really? No, I haven't. I had these status. Which I'm yeah. Just math. Yeah. It's just math. You do physics? Yeah, I'm gonna talk to this about it. You too. Do you have any? You got one? Yeah, from 11. Yeah. Actually, Roger. What is that? Oh, I know.
Gonna be on campus at all on Friday?
On Friday?
No? Okay, so next time is probably Monday, Tuesday? Okay.
All right, so as you guys finish trickling in here, have a warm-up problem for y'all. I believe this was from the reading questions, chapter 11. There's a request for this one. Good warm-up, though, for stoichiometry. Yeah, so this is moles, stoichiometry. Yeah, and then you need a balanced equation, though. Or it's asking for a CO, but yeah. then we have lots of people online today, probably traveling, so if you're in the chat, just make sure you're posting some answers, so help us out, some balanced equations, yeah. Yeah, so then you get moles, but
So if you were able to react all the way with a
then what, say?
in this case, it would react.
Yeah, so we're assuming, yeah, we're assuming complete reaction. So let's see, do we have a balanced equation? And so let me just write out everything first, right? So again, like I mentioned, our exam is just going to be focused on the latter half of the portion, but obviously chemistry is cumulative by nature since you have to know how to write this out. So we have diiodine, so I2 pentoxide, so O5, reacts with, so we have to know, plus carbon monoxide to give iodine, which is hinted at here, but again, right, we have to know it's a diatomic. So make sure your diatomics are starred. And then, Sky, did you want to give us the coefficients on this one? All right, so did everybody start with this? So this looks good. And so now kind of walk me through what's our next step. So, right, it's asking us, so it produces iodine, and it's asking for CO. So what can we do then? Yeah, moles of which one? So I2, so then what's the molecular weight of iodine? So 1 mole of iodine is that for one iodine though?
For one single item.
Yeah, so then what's the diatomic? 253.808, I think you both said. Okay, excellent. So let me get my, And then chat, just make sure that you do the diatomic. So again, it's I2. So I get a pretty small number. All right, so now we're at moles of iodine. And so then what can we do next here? Yeah, multiply by 5, but how you got there, right? So going to our balanced equation. So 1 to 5 ratio. And I'll write it out explicitly. So yes, multiply by 5. So times 5. So now we're at moles of CO, and I see that in the chat as well. And then so last little step, right, it was asking for grams though. And so we're at moles of CO. And help me out, what's the molecular weight of CO? So 28, 12 plus 16. So times 28. And so we should get about 0.0678 there for that answer. That's the grams of CO that were present. So 0.06, yeah, 78. I think officially the online answer rounded to 9 for some reason. Again, slight discrepancy, but you should be able to figure out which one. All right, questions on that one? So I think the balanced equation was probably the hardest part of that one. Just trying to piece that out. Just grams, because it's just asking for grams of CO present. All right, so quick announcements. So did everybody check out the guest lecture? I got a few emails. I just need to make a column still in Blackboard before I start putting your points in. But the guest lecture is on our YouTube channel for the class. If you guys need a direct link, I can post it in Blackboard. I've just been a little slacking on that. But it's there, you can find it. So basically, he took like 2 hours, so you can just watch like the full hour. That's his main spiel. And then like the last hour, the audio gets a little funky because he kind of like walked off camera a bit and was answering questions for an hour. But you know, you can still kind of listen, but you don't have to. So just again, like the main lecture. And then just send me 1 or 2 sentences, just like what was cool or interesting, right? I just want to know that you listened to it. I don't need a whole essay dissertation on it. And then, yeah, just get me, just get this done by the end of the quarter. So no real due date other than the due date of the quarter, whatever that is, December 13th, question mark. Whenever grades are due. No lab today, so other than makeup, so no regular lab. If I could spell, geez. So no regular lab. We are doing makeups today, so if you missed any lab, then come at 1:30. So our normal lab time, so we will be there for makeups. And if you want to ask questions, office hours, that's also a great time as well to just check in. And then, all right, let's try to get through chapter 12 today. So I'm going to try to push us through lecture. And yeah, the lab today is just in our regular upstairs lab, again, for makeup or anything else that you need to make up. If you're missing quizzes or anything, let's get that taken care of. And then no quiz this week since we have a holiday. So, all right, we'll focus on powering through the chapter now. All right, so now we want to go towards solutions. And so it just starts off with a reminder that solutions are homogeneous mixtures. And so remember, a mixture is 2 or more different chemical substances. And we can think about a lot of the mixtures that we've used in lab, right? We've used anything from sulfuric acid to, chloride salts, sodium salts. And a lot of these, right, have been aqueous. And so we can start thinking about these in different components. And so we have our solute component. So that's basically the solid being dissolved. Generally a solid, or it's the minor component. Yeah, so you can have, we'll go over that, all the other different types of solutions roughly. But yeah, you can have any sorts of mixtures. And so, right, our sulfuric acid, our copper, our sodium, that's our little solute. And then in our case, since we're in Gen Chem, our solvent for all of these has been water, right? So all of these have been aqueous. And again, aqueous referring to they're dissolved in water. One of the exceptions, I don't know if you all have noticed this, so next time you play with a phenolphthalein, if you look at it, it's actually dissolved in ethanol, and that's because it's organic, so it can't go into water. So that's just something to think about, which we're kind of getting to. And this kind of gets into this like dissolves like thing, where in general, polar can dissolve polar things. So again, we're thinking about water and our ionic compounds, or perhaps things that do go in. So sugar can go in, right? We kind of have to force it, but it does have hydrogen bonding, which I didn't cover in this class yet. Oops. Or we could also, again, like dissolves like, our nonpolar dissolves nonpolar. So I was trying to pull up. So let's look at fructose for a second. And so like I've mentioned, and we're going to look at a demo. So sugar doesn't really go in that well, right? It's not ionic. It can't be nucleated like a sodium or chloride atom can. But it does have this H attached to an oxygen, and so therefore it can participate in hydrogen bonding, so the water molecule will be attracted over here. So it'll go in, but again, not as well. And so of course, this goes towards entropy, is always happening, right? And so this is, nature has a tendency towards spontaneous mixing. So we'll revisit entropy later, of course, but just telling us that mixing is energetically favorable. So, right, if you put a little drop of food coloring in a glass of water, it would disperse. And so we can think about other types of solutions. So y'all mentioned that. So, right, obviously we can have a gas-gas phase, such as air. So obviously our air is a mixture of gases. We can have a gas in a liquid, like the carbonated water that everybody likes, or soda, of course, beer, any of those things that are packed. And obviously it could also be nitrogen that they use. Liquid, so any sort of drinking ethanol. So it mentions here vodka. And so just for context, so right, 200 proof is 100% alcohol or ethanol, right? And that's obviously generally not sold. And Bacardi 151 is 150 proof, so half that to get your percentage of ethanol. So you can just think about that. And then, right, we can have solids and liquids, obviously. So seawater and many, many others, solid liquids we could go on. And then solid, that would be like your alloys or any metal mixtures. Yeah.
So do you ever say with a solution of plasma, a bunch of gas, or is it only a solution of liquid?
I mean, plasma is a very specific state of matter, so I don't think you're going to have plasma mixing, right? I mean, it's still pretty fringe, so. And so then we can say, right, when something dissolves in another solvent, it's soluble. And so again, right, for our Gen Chem purposes, we're mainly focusing on ionic compounds, and obviously a lot of these salts dissolve in water. And then later you'll go on to organic chemistry, hopefully, and then you'll talk about all sorts of other organic solvents, since that's, again, how organic chemistry is done. I've kind of mentioned that. And so bromine, for instance, is soluble in methylene chloride. This is also known as DCM, so dichloromethane. And other just organic solvents, right? And this is not comprehensive, so benzene, toluene, ether, those are pretty common. And I'll add there, we need a hydrocarbon, so pentane, right, etc. So any organic substance, that's what you're going to be doing your reaction in. So ideally ether, just because of safety reasons, but again, you'll get into OChem and talk about all sorts of different factors to think about when talking about solvents. Yeah.
Does aqua regia fall under any of those categories?
I mean, aqua regia is just more like a cleaning agent. It would be like a solvent, but yeah, aqua regia is just not really a traditional solvent. So aqua regia, we should just talk about it really quick. So aqua regia is a specialized cleaning mixture. So it is a 3-to-1 mixture of HCl to nitric acid. And it should only be used to clean metals, and it should only be used when you're desperate. And so the problem with this is you can't store it, and so that's why I want to bring up the safety point of this. So right, you have to use it, clean it, and quench it. So you can't store it, you can't, anything with nitric, you can't just have nitric waste sitting there, you need to quench the nitric waste. And so horror story from grad school, so not my grad school experience, but somebody else's. So somebody was just happily working in the lab, minding their own business. Boom, explosion goes off, like right at their feet. They had no idea what's going on. Turned out somebody had a bottle of aqua regia just stored there, complete no-no. So yes, it just eventually went off. So yeah, that's why you wouldn't really use aqua regia that much. It was, of course, used to dissolve like gold, famously, like during the Nazis, and when they were like invading. So yeah, people, you can dissolve gold in aqua regia, but otherwise you don't generally want to store solutions of it because they might explode. Yeah, so gold is an element, right? And so that's the problem. It's really hard to dissolve. I think it does go into nitric, though, or it might always take a combination. I can't remember, but yeah, that's. No, it just goes into solution, and then you can recover it back out of the aqua regia. So that's why they did it, to preserve their like metals. So they're preserving like their Nobel Prize-winning chemistry metals. So then later they got them like recasted, but yeah. Anyways, I'm trying to power through this. And so we have seen some times when a substance is not dissolved. And so, right, everybody's probably seen oil and water, right? Just look at your salad dressing this Thanksgiving, and you'll notice, right, the oil's floating on top of the water, right? So that is insoluble. We could also use the term immiscible. So they form layers. So if you kind of force something to mix that doesn't want to be mixed, then you get like a horrible looking cloudy thing called an emulsion. And so what you'll learn in OChem is how to fix an emulsion. So you can use like a brine solution and more organic solvent to kind of force the layers, because you don't want an emulsion in chemistry generally. You want to be able to separate things out based off of solubility. And so eventually we'll revisit this, the types of intermolecular forces. And so this what dictates solubility. But we can go ahead and look at the math of this. So, right, we want to understand, well, how do we classify solutions? How do we express their concentrations? And so, right, we can just say, oh, we have dilute solutions, which this is a very vague statement. I generally consider dilute to be less than 3 molar. Again, that's just more of like safety. So 3 molar is, the edge of where things start to get more dangerous. And so like 3 molar stuff, will burn. And then concentrated solutions, so I would just consider that, again, in general, greater than 3 molar. That's a very generalized statement. But again, anything greater than 6 molar, that's also really concentrated. And then again, right, concentrated solutions are just more caustic, more dangerous. You just want to be more careful with them. And so then let's get into our first unit. And so we've seen this a lot. It's molarity, and now we can actually officially define it. And so it's just the amount of solute per liters, so moles per liters, so make sure you write that. And that's big M with molarity with an R there. And so let's see how we might make a solution then. And so the stockroom does this for us, so we don't have to, which is wonderful. And so we're trying to prepare a 1 molar sodium chloride solution. And so we're going to use a volumetric flask here. So these volumetric flasks are analytical pieces of equipment that are only good for measuring 1 mark. So we would use a 1 liter one in this case if we wanted to make 1 liter. And if we want to make 1 mole of it, that means, a 1 molar solution, we need a liter of it, so we need a mole of it. So we have 58.44 grams sodium chloride. So you want to weigh this out precisely, transfer this in here, wash down any sodium chloride, right, that's stuck on your funnel or on the side. And then you want to kind of dissolve it, kind of fill it up, 3/4 of the way, then shake it. And then it's not shown in this picture, but these things have these ground glass stoppers, so you can cover it and invert it. And then, so right then you'd shake it, dissolve it, get it homogeneous, and then, right, you have to very carefully fill up the water, probably dropping it in with pipette to get it right at that line. And of course you can't go over, because if you go over, now it's imprecise and you got to start all over again. And so that's how we would precisely prepare a 1 molar solution. So let's try these 2 problems. So we'll start with this first one. So if we dissolve 25.5 grams of potassium bromide in enough water to make 1.75 liters, what is the molarity? so let's start hearing. So what do we need to do? So what do we get for our molecular weight? So 119, did people also get that roughly? And so now we can find our moles of KBr. Oh. So then we get about 0.214 moles of potassium bromide, and then we can plug it in to our molarity formula, so it's just moles over liters. So 0.214 or so divided by 1.75. And so what do we get for our molarity? So 0.12, so everybody, so thumbs up for that one. And then make sure you give it 3 sig figs for our numbers, so 0.122 molarity. All right, so go ahead and try the next one. So again, just use your relationship. Molarity is moles over liters. And set up a proportion.
Does that assume that the solution is saturated?
I mean, that's not what it's asking. Because saturated is different, right? So it's just saying that it's a 0.255 molarity solution. So let's look at 2 different ways to solve it. So, right, we can look at our dimensional analysis and kind of look at our equation here. And so we have moles, so 0.255, right, moles. And then if we divide it by the molarities, remember molarity is moles over liters. So your units pop out from there, right? Moles cancels, leaving you with liters. So let's do that. So then we have 2 liters, 2.04 liters. So that's one way to think about it. But if you like proportions, maybe this is a good time to think about proportions and what it's saying. So again, right, we have a 0.125 moles for every 1 liter. So then we're saying, well, how many liters, right, contain 0.255 moles? So I don't know if that's easier for some people to think about, and then you just have to cross multiply and solve, so then you end up with the same thing mathematically, 0.255 divided by that 0.125. So did we all get about 2 liters for that one. And so kind of play with these two methods. Ideally, they should both make sense to you of this unit canceling. But proportions are always a nice fallback with these problems. All right, let's keep it moving unless there's questions. So flag me down for questions. Like I said, trying to keep us going here. And so the next big math part that we should go over is this dilution. So how to make a solution from another solution. And so why this is relevant, well, again, your stockroom does it all the time for us, right? So they may order, concentrated acids like 12 molar HCl or 16 molar nitric. And then we're usually not working, though, with such a concentrated solution. So they have to be able to prepare a dilution. And so this is the formula that you need to know. And this is really all you need to know. So C1V1 equals C2V2, where concentration can be in any unit as long as the units are the same. So generally we work with molarity, but again, any unit would be appropriate. Same thing with volume. Again, generally we're in liters or milliliters, but as long as the units match. So I'll say that. So units don't matter, just need to match. So right, it could be gallons, whatever. Percentages, percent by weight. And so obviously the concentrations and volumes are inversely proportional, but we'll practice the math there. And oftentimes you see it written as specifically this M1B1 referring to molarity. But again, I'm emphasizing to y'all that concentration does not matter. So we'll see other units of concentration eventually. All right, so let's go through this and kind of solve the math. And so we start off with, we want to have 3 liters of a 0.5 molar solution, but we're starting with a 10 molar stock solution. So the first thing the stockroom is going to do is figure out, well, how much of this stock solution do I need? And so we can plug it in. So I'll plug in my 3 liters and 0.5 molars on one side. And then we're trying to figure out, right, our V2 of our stock solution of 10 molar. So now just doing our math. So 3 times 0.5 divided by 10. So now this is in liters. So we have 150, I'm going to convert it to milliliters just because that's easier. And so now we can think about how they would physically do this. So then you measure out your 150 milliliters of your stock solution. So you want to transfer that right to your volumetric. And now we're using a 3 liter volumetric. And then I'd probably dilute it, a little bit, shake it up, and then finish diluting it all the way, and then again invert it some more to make sure it's all mixed and homogeneous. And so again, right, you go very precisely and slowly all the way to your 3 liter line. Yeah, let me. So it should have been 0.150 in your calculator. And then I just converted it to milliliters.
What's the benefit of the shaker volume last one? There's a sort of bowl shape too.
I mean, it's just easier to swirl since it's so long neck, so it helps you mix and invert it. But otherwise, I'm not really sure the full history. All right, so now we can get into types of aqueous solutions. And so again, we're thinking of salt versus sugar. But so what's the big difference again between salt and sugar? Just again thinking really, really basic. What type of compounds are they?
One's ionic, one's covalent.
Exactly, right? So salt is ionic, okay. Sugar is covalent. So that's already, right, a difference right there. And so let's now think about it. And so what happens right when it dissolves? So we've kind of talked about it, right? So we've talked about these attractive forces that are holding the solute particles together, right? So we've kind of looked at those electrostatic forces. And so now we're saying, well, what has to happen, right? So obviously we have our salt crystal. So these would be the solute-solute interactions, again, our electrostatic forces. But then to get something to dissolve, right, our solvent has to come along and overcome these solute-solute interactions, right? So our solvent-solute interactions have to be stronger. And so again, if those attractions then are strong enough, dissolving happens, like we see with sodium chloride or, again, all our other compounds. And so kind of think back to your solubility rules that you have. And so, right, that's why we have these rules and these trends. And again, right, they were determined experimentally. Like I mentioned, we'll take a deeper look with the solubility stuff. I think second quarter will quantify it. But, right, we're just at least kind of thinking about what has to happen, right? And so it's not always obvious if that solvent-solute interaction is going to be stronger than the crystal. And so that's why you start getting things like insoluble compounds, right? So obviously those solute-solute interactions are a lot stronger, or at least that's what it's perhaps hinting at. And so we've seen this picture. We're going to keep seeing it. And right, we have our oxygen. So like we mentioned, it's electronegative. We can put our lone pairs on there as well to remind us that it has lone pairs. And so again, with our ionic compounds, this is going to be attracted to our positive cation side. And then leaving our hydrogens, and obviously colored in blue here, with our partial positives. So this is going to be attracted to our anions. And so then it's going to surround and nucleate them. I forgot my water molecule models today. Maybe I'll grab them during the break, just so you can kind of see really how, again, it's going to nucleate and surround it. And so that's what's, again, depicted here. So just the water overcoming our solute-solute interactions between our sodium and our chloride. And so then, right, this results in our solution. And obviously, right now, they're moving around. So we're going to see that in the demo that I have set up, that now salt can conduct electricity, right? So we mentioned bulk salt can't conduct electricity. It's just a crystal. There's no physical movement. But now in water, right, those ions are floating around. And so now we're getting into why I dragged out half the chemistry lab, it feels like, to look at these electrolyte and non-electrolyte solutions. And, well, what is this defined as? Some materials that dissolve in water to form a solution that will conduct electricity are called electrolytes. And so basically this is implying that we need some ions. Again, generally ionic compounds, but we'll talk about the other kind of situation. And so we'll compare this to sugar. So again, we mentioned, right, we can kind of force sugar into water better if we heat it up, but it still kind of goes in. But we mentioned that sugar was covalent, aka it's going to stay as one big discrete molecule, and so that we'll find that it does not conduct electricity. so we'll get past this text, and then I'll do stuff for y'all. And so again, electrolytes, we mentioned that they have to completely disassociate. So again, this is anything that is soluble, right? So you might have to look at your solubility chart, make sure it's soluble. Okay, if it's soluble, that means it's completely disassociating. So calcium chloride, soluble, so it disassociates into calcium, and then 2 equivalents of chloride. Now let's talk about this weak electrolytes. And so they drew formate up there, but I just don't like formate because nobody knows what the heck formate is. And so let's look at acetic acid, or back to these, right, organic acids. So we mentioned that these organic acids have this carboxylic acid group. And so with that, they have some sort of equilibrium. And so again, these weak electrolytes tend to be organic compounds that are acids. And so again, right, they have an acidic proton, and then all we're saying is that there's some sort of equilibrium, and again, we're going to see that with the acetic acid. And so the acetic acid partially disassociates into, don't forget this is acetate, and then H plus or hydronium. So I've already gotten lazy, and right, I'm not writing hydronium. I just want to emphasize, right, H plus doesn't actually exist on its own. It forms hydronium. And then to compare that to a strong acid, and so now this is getting into a little bit of acids and bases, but again, we're just wanting to distinguish between strong and weak. And so strong acid, so hydrochloric acid is a strong acid. And again, it has nothing to do with how dangerous it is, but rather that it disassociates. So there it has vinegar. And then I do want to bring up, so HF is surprising to people because HF is actually a weak acid. And you know, you may not think of that because HF is actually pretty dangerous. So HF is, so I work with like a ton of dangerous chemicals in my grad school era. And I would put HF as really close on the top of my list of, I will not work with this, probably unless I absolutely have to, but I probably don't want to work with that. And so why you don't want to work with HF, so now time for another safety horror story, is that, so HF, apparently it doesn't burn that much when it gets on your skin, so you may not notice if it gets on you, but HF will go through, and then, right, it can dissolve your bones since it reacts with the calcium. And so the problem with that is, okay, well now that calcium can re-solidify somewhere in your body, right? So obviously, you guys probably have taken more biology than I have at this point, or more recent. So if it solidifies in your head, you can have an aneurysm or something, in your heart attack. You know, if you're lucky, it solidifies somewhere and you don't notice it. But that is the danger. So if you're working with HF, they have this special like calcium cream. So if you are accidentally, you know, exposed to it, you put it on right away, and you know, hopefully all the HF reacts with the cream and not your body. But yeah, so HF is pretty dangerous. And then obviously it has a reputation in films, right? They're always dissolving bodies in HF. And but HF too dissolves like glass, so it's a pain in the butt because you have to store it in like a plastic thing and not glass because it'll eat the glass. So.
You can burn through your body and your bones. It makes it a weak acid.
Well, exactly this, the fact that it does not fully disassociate. But that's what also makes it even more dangerous in some ways, because then you have the unsuspecting chemist sometimes, like if you have a young chemist, and you know, let's say they're using a sodium fluoride salt, or any sort of fluoride salt. The problem with that is if you don't neutralize it, it can reform HF. So that is a big danger. And so that's, again, going back to the weak part, is not how dangerous it is, but the fact that it can go back and forth in this equilibrium. So then you have these fluoride salts, and then that can become a danger because those can form HF. And if you're not thinking about it, you know, then you got a danger there. So that's a hazard, and you'd want to neutralize your waste solution if you have worked with any sort of fluoride salt to eliminate any possibility of HF. So, anyways, all I have to say is that it's a weak acid. All right, let's light up the light bulb before we take a break. Let's see, let me pop this out for the class. Okay, trying to do advanced camera work here. All right, so now let's explore what we just finished talking about. I really hope I don't electrocute myself today. And so what we're going to be doing is completing the circuit, right, to see what is an electrolyte and what isn't. And so why I made a joke about electrocuting myself is, right, you can obviously complete the circuit. And I did that last year when performing this demo. And so you always want to handle it one-handed, because you wouldn't want to complete the circuit, right, with both of your hands, because then that's running across your body. So when I did it last year, I just did it with one hand and shocked myself. It was just painful, but I don't want to repeat that. So, all right, let's start with water. So I just have plain water here, so nothing in solution. And oh, nothing happened. Right, that's about what we expect. So now I'll try to dry this off a little. So cleaning it is how you shock yourself. And then, so let's light it up. Let's do, so there's salt water, right? So I didn't bring salt, but just, okay, we have brought plain salt. It wouldn't do anything. Again, no movement. Let me try to rinse this off. I stick it in the sugar. And so now let's compare that to sugar. So, okay, we said sugar was our non-electrolyte. And yep, that's true. So I shoved a ton of sugar. You can see that there's a ton of sugar at the bottom, but nothing's happening, right? Because again, the sugar is not disassociating, so there's no ions floating around. And so now let's compare. So you can tell I don't want to pour all this out. So now this is acetic acid. So this is 4 molar. And then we want to compare it to, so I brought sodium hydroxide. So that is a strong base. Again, completely disassociates. So this is also 4 molar. And then I apologize, I didn't have a 4 molar acid solution, so I grabbed the 3. So that's a close enough comparison. And so now let's see. So let's start with the the acetic acid, acetic acid. So again, we said this was a weak acid. And so, right, a 4 molar solution barely lights up that bulb there. So not that impressive, perhaps. So let's compare that to the, let me rinse this a little better. Let's compare that now. So same strength, right, same molarity. Look how much brighter, though, that sodium hydroxide is, right? Because that's fully disassociating. So strong base, fully disassociated. And then we'll try the last one, the acid. Let's try to rinse the base out of here. And so now the last one, so our 3 molar HCl. So right, even though I couldn't get it a 4 molar, obviously a lot brighter than the acetic acid, again, because we have complete disassociation. All right, so that was fun. That was all my demo I had for y'all. All right, so I think that's a good place to take a break. And so, right, just that's what's shown here in the little pictures, but hopefully that was more fun seeing it live. I'll leave it up here, so if you want to play with it during the break and stick the light bulb in, we can do so. And then otherwise, yeah, let's just meet back here at about 12 02 so we can keep powering through our solution chapter.
Wi-Fi on that. We got the military Wi-Fi. So you put moles in and you multiply by 5. It's a ratio. Yeah.
All right, I think we all made it back. Maybe one straggler. And so now you can kind of, right, see where we're going with this. So of course, we did stoichiometry last week. So now we're going to want to do stoichiometry of our solutions. I lost my pen apparently. Oh, there it is. And so again, right, they tell us molarity, so moles over liters. And so, right, just emphasizing, there's our moles again. And so, right, we will use this to find, whatever we need. And so, right, this is just emphasizing, well, how do you get from moles, right, if you're given volume and concentration? And so that's all that's shown here. And so, right, first step is just to emphasize, well, you need to convert. So, right, again, molarity is given in moles over liters. So if you're given milliliters, convert to liters. and then you can just multiply it right by your molarity to give you your moles. So that's what's shown in this step, right? So then they just walk you through the math there. So now let's go ahead and take it to stoichiometry, right? And so now we have what volume, it's asking in liters, of a 0.150 molar potassium chloride solution will completely react with a 0.150 liter solution of 0.175 molar lead nitrate. And so we have the balanced equation. So start thinking about how would you solve this, right? You know everything, right? We know how to get moles now. I'll scroll back up, right, from our molarity. Let's see if you can start this. And again, chat, post answers to help us out. So let's start hearing, so what do we have to calculate first? So what do we start with? So you're looking at the lead nitrate? So yeah, so we want to find moles of lead nitrate. So find moles of that. So then you're telling me, so we have 0.15 liters, and we're given the molarity, and we can rewrite that as moles over liters. All right. So then we can multiply it. All right, so then do we get 0.02625 moles of lead nitrate? And so now what do we do with this number? So excellent, so we looked at our equation, so let me just moles PB nitrate here. And so yes, just being explicit. So 2 potassiums for every 1 lead nitrate. So looking good here. And so now we can say, well, we need 0.0525 moles of potassium chloride, right, to react. But it's asking us for volume, so we're given molarity. So what can we do now?
You can divide the molarity, the concentration by the total amount of moles you want. And that gives you the number of liters.
So, yeah, I feel like you said it backwards. Yeah, because we want to divide by 0.15, so that's moles over 1 liter. Or again, I think the proportion may make more sense for some people in this case, right? So again, we have a 0.150 moles for every 1 liter. And so if we want 0.025, cross multiply. So either way, we're seeing, okay, we need to divide this by 0.150. And so then this gives us 0.35 liters of our potassium chloride solution. And I'll give it another sig fig. But did we all get that at the end there?
What does lambda represent?
My X here.
Okay.
Any other questions on this one? So I feel like that went pretty well, right? So I think y'all got the idea, right? We just have to find moles, then back to our mole ratio. And then in this case, right, for moles to liters instead of grams there. So that was good. All right, so let's look at another essentially type of reaction, but this is just kind of a fancy specialized term. And so we are not going to do acid-base titration this quarter, so we'll save that for later. And so a titration is just basically where you do this acid-base neutralization reaction, and you may titrate it with another substance. So like I said, y'all will do this later. What you'll do is, it's called KHP, but this is a standard, and then you'll use it to figure out the molarity of NaOH, and then you'll use that sodium hydroxide solution to figure out another solution. And all that really being said is it's just a bunch of stoichiometry equations. This is just kind of showing you how we do it. And so you have to have an indicator. So in general, we use the phenolphthalein, since it has a transition around 8 or 9, so that's a good base indicator. So usually you're doing an acid-base titration, so dropping a base into the acid and then trying to get a nice pale pink, and that would be the color right before the equivalence point as it goes more pink. And so this is what's meant by the endpoint. So again, that's what I was talking about, pink. So the pink would be our endpoint. And again, if you had another indicator, or we're trying to do other points, right, obviously your endpoint depends on your indicator. And so, right, your indicator is usually selected such that it's at an equivalence point. So this is more relevant if you're doing like a triprotic acid, but we'll save those thoughts for later. And so, again, we just want to appreciate the basic setup. So base is in the burette. These have little millimeter markings, so you can, of course, estimate just like we normally do to 2 after. And again, you would look at your burette in lab, and then you have your little stopcock. So if it's parallel, or excuse me, perpendicular, it's not flowing. Parallel, it is. And then nobody likes titrations because you have to go really, really slow. And once you do it, you'll find one drop can turn you all the way dark pink. And so this is somewhat how a titration goes. And again, the phenolphthalein turning pink. And so now we can do the math behind it. So it says the titration of a 10 milliliter sample of hydrochloric acid solution of an unknown concentration required 12.54 milliliters of a 0.1 molar sodium hydroxide solution. So what is the concentration of the unknown hydrochloric acid? So just think about how would you start this. Might want to start with an equation first. No, let people think for a second, and we'll go over it. Yeah, so what's your balanced equation? So I have one in the chat, but so yeah, let's start with that. Does anyone have our balanced equation? Yeah.
So 1 HCl plus 1 NaOH equals 1 H2O plus 1 HCl over the time.
Excellent. So that looks good, and chat agrees with you. And so really the key point is that the HCl and sodium hydroxide are in a 1-to-1 ratio. So we're seeing that with this balanced equation. And then maybe take another minute or two. So now that we have this, right, think about what we need to calculate. So get moles of NaOH, right? That's equal to how many moles of HCl we neutralize. So then what was the concentration? And so right now we can find moles of sodium hydroxide. So what do we do for this one? Because it gave it to us in milliliters. Divided by what? Well, we got to divide it by 1,000 first, right? to get it to liters. So 1 liter is 1,000 milliliter. And so then now we can multiply it by our molarity, right? So 0.1 moles for however many liters we have. So 12.54, convert to liters times 0.1. So then do we get 0.001254 moles of NaOH? And so now we have volume here, right? We have moles. And so now we can figure out our concentration of HCl. So again, 1-to-1 ratio of NaOH to HCl. So now we can say, well, we have 0.001254 moles of HCl, and that was in 10 milliliters. So convert that to liters, right? And we have our molarity. So 0.010 liters. So then we have a 0.125 molar solution of HCl. Does that make sense to everybody? Yeah. So back to the balanced equation. So that was probably the easiest way to see it. Yeah. Yeah, so let me write that just so it's clear. So this was, right, moles of NaOH that we found, and then 1-to-1 ratio, but then we can just take moles over the liters that we had and get our concentration. Let's see, do we make it through? So I think we actually made it through this chapter. So now we can just focus on the math part. So let's do another stoichiometry practice. You can tell I stole this from Everett Community College, but I like these. You just can't trust the solutions all the time. Sometimes they have typos. All right, so let's look at this equation. So they gave us a balanced equation here of magnesium hydroxide plus hydrobromic acid gives us magnesium bromide and water. And so then you can look at, so how many milliliters of a 0.225 molar HBr solution would be needed to react with 3.26 grams of magnesium hydroxide. So start trying to figure that one out. And again, chat can post helpful things, molecular weights. Yeah, well, it's usually like a titration / neutralization, yeah. So that's like why you get the water, yeah, yeah. So how's this going? Kind of where did y'all start? Yeah,
There's 3.26 grams.
all right, so yeah, let's do that. So what do you get for the molecular weight of magnesium hydroxide? Yeah, so you said, because we need to take 3.26 grams, divide it by the molecular weight of magnesium hydroxide. Yeah, and I see that in chat too. So that sounds good. Did everybody get that? So that's our magnesium hydroxide. Gram per mole. All right, so then we have moles of magnesium hydroxide. And so where do we go from here? So then you did, so I might set up a proportion. So we have moles. So we should do, so let's do over X, right? So then, well, hang on. I think we skipped a skip, right? So before we turn this into solution, because right, we're at moles of magnesium hydroxide. But then what's our mole-mole ratio between them? So 1 to 2. So then we need to multiply this by 2, right? So for every 1 mole of magnesium hydroxide, 2 of HBr. So times 2. And so now we have 0.1117 moles, right? We have a 0.225 molar solution. And so I might just set up a proportion for this one. So 0.225 moles for every 1 liter. So we need 0.112 roughly moles. So how many liters is that? So we need to divide by our molarity. And so we get about 500 or 497 milliliters. Questions on that one? Did we get that answer? Let's try some other types of problems. So we'll do something. So we haven't quite talked about weight per volume and all that. We'll mainly focus on molarity. Let's practice a basic one here. So then how many grams of magnesium cyanide are needed to make 275 milliliters of a 0.075 molar solution? Sorry? Yeah. Yeah. So how's our problem looking? So how do we get moles of magnesium cyanide? So milliliters to liters. Excellent. So 750 milliliters, 1 liter, 1,000. All right, and then we can probably multiply by our molarity then. So 0.075 moles per liter. And then what was the molecular weight of magnesium cyanide that we calculated? 76.34. So I see that in the chat, or 341. And so if we have, did we all get this many moles? 0.0206 moles of magnesium cyanide. And then now we can multiply it by the molecular weight. So moles times 76.34. You said 1, right?
Yes.
So grams. And so about 1.57 grams there. So I see answer in the chat. Everybody got that here as well. Let's look at some other ones. Let's practice. Let's do a dilution one. Let's just try this first one here. So we have 45 milliliters of water are added to 250 milliliters of a 0.75 molar potassium sulfate solution. So what's the molarity of the diluted solution? So how's this problem going? So what was the kind of tricky part in this, right? Because they gave you your C1, they gave you V1, but they didn't really explicitly give you V2. So what's the V2? Yep, so that's a tricky one. So watch the wording, right, on those problems. So that's good. You didn't get tricked there. So, okay, 295 is our new V2. And so now we're ready to do our math. So C1 V1 equals C2 V2. I'm going to leave it in milliliters just because that's fine as long as, again, units are consistent. Oops. And so then what do we get for our new concentration? So do we get 0.64 molar and only 2 sig figs? So 0.64 molar solution. So it just depends like what it's asking for, right? Because this one was just a dilution one, so there weren't like any other equations involved, any other chemicals. So yeah, usually that's your hint is like something plus something. So then you're doing problem. Oh, 0.64. Sorry?
I was doing something, some other kind of math, like, I was seeing it in the,
So did it work?
there, 6.63599.
Yeah. So let's try, we'll do some more. So let's do another stoichiometry one. But we'll change it up a hair. Might have to write this one somewhere else. And so if it takes 38 milliliters of a 0.75 molar sodium hydroxide solution to neutralize 155 milliliters of sulfuric acid, what's the concentration of sulfuric acid? And so just watch out. Start with your balanced equation, and then we'll go over it. So let's at least check in. What was your balanced equation? Because that was the tricky part of this one, or a little different than we had seen. Yeah. Yeah. Sodium sulfate. Excellent. So this looks good, and I see that in the chat as well. And so, right, that's a big difference from our last neutralization, right? We had our HCl, which was monoprotic, and so this is diprotic, so now it's 2 to 1. Yeah.
Why is it a sulfate instead of a persulfate? That's for oxygen.
No, I mean, that's just the naming. So then I'll give y'all another minute or so to just kind of finish up the calculations from here. All right, so finish walking me through the end here. So what do we need to start with? What should we calculate first?
Give the concentration and volume of sodium hydroxide to 3%.
Excellent. So let's do that. So I'm just going to convert this. So 0.038 liters now, multiply by our molarity. So again, moles over liters. And let's see what we're starting with. So 0.038 times our concentration. All right, so it looks like we're starting with 0.0285 moles of sodium hydroxide. And so where do we go from this point? So mole to mole ratio, so it's a 2 to 1 sodium hydroxide to sulfuric, so we need to divide. So 2 sodium hydroxide, 1 sulfuric. So divide by 2. So then that gives us, right, moles of sulfuric acid. And so then what's our concentration? Well, looks like we're at the home stretch. So right, we have moles. So let's just write this out. So moles. And so what do we have to do? So we're asked concentration, we have volume, we have moles. What do we divide it by? Yeah, you divide it by, right? So think back, what's your concentration? It's just moles over liters. Well, we have moles of sulfuric, right? We have liters of it. So we just have to divide, right? Except convert this to liters. So I'll just rewrite this, and I apologize since there's hardly any space for work. So point. So let's divide. And so then I get the concentration as 0.092 molarity. All right, so not too bad. I just want to point out, so we'll probably have to revisit solutions kind of later as we continue on, just through the course. So I wanted to point out, so if you look at page 7, this concentration worksheet, it has stuff that we didn't talk about explicitly. For instance, it mentions like this molal. So molal is little m molality, and that's moles over kilogram of solvent, but we don't really use molality too much. And then eventually we should maybe practice these kind of other percentages. But a lot of these you can kind of puzzle out yourself. You just kind of have to really pay attention to the units, right? So for instance, like this one's a volume per volume. And, you know, sometimes you have like weight per volume, you'll see, or like, you know, weight per weight or mass per mass. So you just have to see kind of what's being given to you and kind of how to work through it. So we'll probably have to do more practice on your exam. Only expect molarity though. So that's the only concentration we're going to focus on. But I'm just trying to make you aware of, you know, there's other units of concentration. We'll talk about them later. Your exam is only focused on molarity. But that's kind of what that is. So you could look at this and, like I said, piece through it. Anyways, we're probably out of and over time, so enjoy your Thanksgiving break. If, again, makeup labs are going on today. Otherwise, go home, enjoy your afternoon.